Good morning, everyone. I hope you are doing all right and ready to learn some physics. So here in this corner of the slide, I wrote about our midterm next week. So just like it's written in syllabus, it's going to be next week. And I'm suggesting this to study for the worksheet, for the midterm. So understand the worksheets in this order: worksheet, everything, and then clicker questions, understand them, why particular answer is correct answer, and then problem done in the class. I don't ask long problems. So if I ask long problem, it's going to be just a part of that long problem, maybe drawing free-body diagram or just writing equation, something like that. Okay. So there are going to be some problem and there will be conceptual questions, just like you have seen in the clicker questions. So there will be, I think, around 25 questions. All of them going to be multiple choice questions. But to answer some of those questions, you have to actually write down the equation. And in some cases, you may even have to plug numbers, one or two problems with numbers. But mostly, it's going to be about the, the physics, equations, and then using them to answer questions, just like we do in clicker questions and so on. Okay. So with that said, so we finished kinematics and then we moved to the dynamics. So in that case, we learned 3 laws of physics and then learn how to use them. So since using Newton's laws of physics, or let's say Newton's laws of physics, both first and second, is about not just about a force, but some of the forces or net force. We need to draw those forces before we can use them. And we use them along the horizontal and vertical direction separately. And for that, we write equations, something like this along the x direction of our choice, and then y direction of our choice. So that's what we learn. So to unravel this part of the equation, we need free body diagrams drawn something like this with axis marked. Okay. So we looked at the application of these equation in several situations, like in vertical direction, in incline plane, and so on in the last class. So today we will start by talking, using the same idea for 2 connected objects. Like when we have elevator, for example, what happens? It has one mass here, another mass that accelerates up and down. So in that case, both masses are attached to a string that passes through a pulley. So simplified version of that is called Atwood's machine, and it has 2 masses connected. So when we have to use this, Newton's law, in this kind of situation, what we do is we draw free body diagram for each of those. I think we went through, this one quickly last time towards the end of the class, but let's see. So there is this free body diagram. So these are like 2 elevator. One elevator, let's say when one is accelerating up, another one is accelerating down. Since they are connected, their accelerations are same, okay? And as long as this pulley is small and friction is negligible, the tension, value of the tension in one rope versus another rope, both of them are in same in terms of value. And looks like direction is also both of them, for both of them, direction also going to be pointing up, no matter whether mass is going up or down, just like in case of elevator. Oh, yeah, this is elevator, and this is also like another elevator. Okay, so when we have more than one objects, then what we do is we draw a free body diagram of both objects, and that's what I am drawing here. And there is this acceleration is drawn on the side, so that we can use that use that information while writing the Newton's second law. Here it's accelerating, so that means net force along the vertical direction is equal to mass times acceleration. And we repeat that for both masses. And that way we're going to have up two equations. So those two equations can be solved for up to two unknown quantities. And if you remember from algebra worksheet, there were these two equations, and that came from actually like this one. So one equation was something like this. Okay, so this is like elevator situation where sum of the forces along the y direction means there are two forces. So here we are putting subscript in mass because there are two masses, so we need to differentiate them. And the mass that is accelerating is m1. That mass we're talking about, object of interest for this particular free body diagram is m1, so it's going to be m1 and times acceleration. So the t and this term here, acceleration, has a positive sign because we are choosing up as a positive. Okay, so this is one equation. And let's say if I want to solve for tension or acceleration, I can start by solving this one for just tension. It's simpler that way. If I solve this one for acceleration, this mass has to go down here. It's going to be in fraction, so I'm just keeping in tension here. And I'm repeating this for mass number 2. Okay. And notice how I always start by writing the main formula that you can find in formula sheet. Okay. So in this case, the situation is same. Two forces are still pointing in the same direction. Only difference is that the acceleration is down, pointing down. So this term picks up the negative sign. So now to solve for, let's say, acceleration, what we can do is we can replace this tension by the tension we got from mass 1, because the value of the both tensions, they are same, right? So instead of this tension here, I am writing this m1 times g plus m1 times a. That's what you see here. And then I'm copying rest. Okay. So now to solve, looks like we need a little bit more room. So I am copying those equations here. So this was the last equation we looked at it. So let's say if I want to solve for acceleration, there is acceleration here and there is acceleration. Before I can solve for acceleration, I need to have just one acceleration in the equation. So to make that happen, I'm moving this in this side. So I'm copying M1A, and then I'm writing this M2A that I moved from this side. So it has negative sign. When I move to the left side, the sign changes. And now this M1Z and M2Z, I need to move them to the other side. M2Z has a negative sign, so when I move to other side, it's going to have positive sign. And M1Z has a positive sign, so when I move it to the other side, it's going to have negative sign. So now still the A is in two places. So to make it in one place, now what I can do is I can factor A out. So this becomes M1 times A times M1 plus M2. So if I were to open the parenthesis, I recover this, okay? So I haven't made any changes. I'm doing this because I know I'm solving for A, and to solve for A, I need only one A or A only in one place. And because of that, I'm factoring that, okay? Right-hand side, nothing has changed. So I can just copy or make it look a bit neater. I can factor G out. I don't have to, but I like that way. So this A becomes M2 minus M1. I am copying the right-hand side times G. And then this M1 plus M2 is multiplying A. So when it moves to the other side, it's going to divide. So that's the acceleration, folks. So either this way, or you can just write without factoring G if you like. Okay, so that's acceleration. So now let's say I also want to find tension. So for that, I can use one of these two equations that has T in it. So I copied this, the equation on the that came from the mass 1. So I'm using this, but you can use the equation that came from the second mass if you like. So since T is already there, I'm just copying that T right there, and there is M1G, so I'm just copying that. Now there is M1 times A, and this A gonna be this whole thing, okay? Or this thing, depending on what you like. So let's use this one here. So M1, so I have this M2 minus M1 times G on the numerator, and then M1 plus M2 in the denominator. So now I have one term here, another one bit complicated term over there. So this is two terms. So yes, it looks a bit complicated, but it is nothing more than, let's say, adding, let's say 2 plus 2, 2 divided by 4, something like that in arithmetics, right? So if I want to add this with this fraction, I want to make this fraction with the same denominator before I can add them, okay? So for that, what would you do? Maybe you want to multiply by 4 and divide by 4. So that way you're not changing anything here, but by writing this way, you made this denominator same. So that way you can just write one common denominator as a LCM. So this becomes 8 and this becomes 2. So I can add them and this becomes 10. So this is one way. But let's say if you like, what you can also do is you can first factor this 2 out. See, there is this 2 and there is this 2. So you can also factor this 2 out before you are adding it. Okay? And then now just add this. So there is no 2. So multiplying may be even easier. Okay. So I am using this here to make this a bit simpler. Why? Because I see there is M1G and there is M1 times G over there too. So I can factor that out. That way when I'm adding fractions, it's going to be a little bit simpler. Yeah, you can just work from here. It's just fine. But to keep things a little bit simpler, I am factoring M1G out. Means this M1G and M1G also going to go from there. So what's left is this M2 minus M1 over M1 plus M2. So now I'm going to go and do the regular add operation. So for that, I need M1 plus M2 on the top here, M1 plus M2 on the bottom, because I want this in the bottom. So for that, I need this one on the top as well, so that the ratio is still 1 because they can cancel. Remember this. We can cancel these to 1, right? Oh, I should have positive sign here. So now over here, what I have is M2 minus M1. I'm just copying the second term here. So now what happens? I can do M1 plus M2, just one denominator. It's a common M1 plus M2. And then this plus times M2 is plus M2. And this plus times negative M1 is negative M1. And you can see here all of these are in the numerator. So that means this M1 has a positive sign, this M1 has a negative sign. So if I add them together, the result is going to be 0, just like 2 minus 2 is 0, right? So, but this one is M2 and M2. So that means it's going to be 2M2. So M1G is already out, and 2M2 is in numerator. And then this M1, M2, M1 plus M2 is in denominator. So I can put that right underneath everything. Okay. So now so that's the basically tension, but I can rewrite this to make it look a little better. So I will write the constant first, so 2G, and then M1, M2, M1 plus M2. So you see the acceleration and tension depends simply on two masses, right? So for example, let's say you want to put an elevator in a building, and you know usually what's going to be the load of the people on the elevator. That means you can determine the mass, total mass of one elevator and another mass that should be hanging for optimal acceleration. Okay. And then you can choose a suitable rope that does not break. Okay. So you can calculate tension for those masses. So you can design elevator that way. And of course, there are this kind of setup even in the windows. Okay. So anyway, I wanted to go through this algebra a little bit because some of you, were a bit stuck in some of the cases. Okay. Yes, many of you did wonderfully well, but some of you were kind of bit stuck while doing the algebra. So I showed you. So this is multiple steps in this problem. Okay. So it may look difficult, but if you understand the process, it's not that bad. We just draw two free body diagrams and write two equations. And after that, we just solving two equations for two unknowns. That's all we are doing. Okay. So now with that said, let's move to our actual today's regularly scheduled class. So we've been talking about friction. We said, okay, something is when something is sitting on. So for now, let's forget about this. So if something is sitting on a horizontal surface, and if you're not applying any force, then what happens? If something is not moving or not trying to move, then friction force is 0. That's what we said. And in this case, that's what's happening. Nothing is pushing or pulling this. So that means applied force 0 means 0 friction. And remember, this is sitting on horizontal surface. So it's not moving and it's not trying to move. So friction is 0. So 0 applied force means 0 friction force. So we can write the relationship between or show the relationship between friction force and applied force when object is not moving. Okay. So when applied force is 0, then the friction force is also 0. So I'm plotting friction force on vertical axis and applied force in horizontal axis. So my 1 point would be something like that. So now let's suppose I apply the force. I push a little bit with some bit of force. Then what happens? Let's say the object is still not moving. So like, think about you are trying to push a couch, okay? So you apply force, or let's say a little kid applies force, the couch does not move. So how much is the friction force in that case? So since there is applied force, what happens is that force is balanced by the friction force. That's why the couch is not moving, okay? So the applied force and friction force is same. And if you gradually increase that applied force, eventually at one point the couch you will feel like, oh, it's almost moving, it's about to move, it's just moving, or something like that. Okay. So until that point, what happens? Applied force and friction force, they are exactly equal. So that means this line passes through the middle of these two axes. Okay. Showing that applied force and friction force are same. And then at the point where this couch is about to move, or just moves a little bit but actually hasn't actually moved, so that's the situation when this friction force is maximum. So since the object hasn't moved completely yet, this kind of friction force we call static friction force. Static, friction force that arises when object is in static condition. Okay. And we've been denoting friction force by lowercase f. And since this is static, we're going to put subscript s for the static. And the static force can be anywhere, static friction force can be anywhere from 0 to some maximum value for given two surfaces, okay? So for example, if couch is sitting on a, floor that has a, carpet, pushing this is going to be more harder than when it is just sitting on wooden floor, okay? So it depends on the nature of the surface as well. So for given two surfaces, there are going to be a maximum value of friction force. And that maximum value of friction force we call maximum static friction force. Remember at that time now, if you were to increase even a little bit of force, it will just start moving. Okay, it's that threshold or critical condition. So that's what that is. And since this is a particular value, that maximum value, sometimes we may write this max subscript on next to this static, okay? So when that's the case, what happens is it depends on two things. So we can write the equation for that. Turns out it depends on two things. One is normal force. You already know, okay, if something is sitting on the surface, so there's going to be this normal force. Another one is this a constant value that is determined by the nature of the surface. Remember, carpet versus wood and the couch. So although it's the same couch, normal force on the couch is same, but friction force on the couch is going to be larger when it is sitting on a carpet versus on a, wooden floor. So how do we differentiate that? So to differentiate that, we use this quantity called static coefficient. Where is coefficient? Looks like I didn't write that. So coefficient of static friction force. Okay. So we call that coefficient of static friction force. And for given two surfaces, the value of this friction force or the coefficient, I should say, can be determine by doing simple experiments, by measuring the force you have to apply to push or slide the object just to start, sliding object, measure several values, for, let's say, and then make a plot, and from that plot find the slope, and that's going to give you static, this coefficient. So this being the ratio of two forces, for example, if I were to solve this one for this static coefficient, what happens? This is a friction force and this is a normal force, means it's the ratio of two forces. Both of them have same unit, means unit cancel. So the coefficient of static friction force doesn't have unit. So it's a unitless constant. Its value is between 0 and 1, okay, for most surfaces. So often students forget to differentiate between this coefficient versus friction force. So coefficient and friction force, they are related, but they are not same. To get friction force from coefficient, given coefficient, let's say, you need to multiply that by the normal force. So you may have to find normal force, writing equation just like we've been doing, okay? So that is about the static. So you give a push to couch. Once it starts sliding, what happens is you don't need to keep pushing with exact same amount of force. Even if you apply a little bit less force, it will just keep sliding. Turns out that's the case. I don't know if you have ever noticed that. Starting to slide is more difficult than actually keep that one sliding, And so why is that? When we do the measurement, it turns out the force that we have to apply is a bit less once the motion begins. So the force is now fixed. See how the static friction force goes from 0 to some maximum value, but the kinetic is always same, fixed, which is less than the maximum value of static friction force. So that's why keep pushing it is a bit less. So why that's the case? Because the friction coefficient itself is a bit smaller. So for that reason, what do? Is we write equivalent equation here for the kinetic friction force, we call it, okay, once object is sliding already, we call it kinetic friction force. So that means now the friction coefficient is different. See that? K subscript versus S subscript. So kinetic friction coefficient for any two given surfaces is always less than static friction coefficient. So that's why the force is also small for the same size of the object. Okay. So we have now two kinds of friction force. One static, which applies from when object is trying to move to just starts to move. And then once it's moving already, then we have kinetic friction force, or two kinds of friction force. Now, why there is friction force and why there are different kind of friction force between two different surfaces, okay? So to answer that question, we have to go all the way to the microscopic level. And probably I already said, before as well, all objects are made up of atoms or molecules connected by bond, chemical bond. That chemical bond acts like a spring, like this. If you try to pull them apart, what happens? The spring pulls you back towards its equilibrium position. So it's that force, spring-like force from the bond, that gives you this friction force in the molecular level. That's what I'm trying to show you. Let's say there are these spring from, some atoms or molecule from upper surface, and there are from the lower surface. So when you putting one object, another object, what happens? It's like a, let's say, two spring mattresses without any mattress on the top, just the spring frame on top of each other. So the spring gets tangled, for example, if you try to separate them. So that's what's happening here as well in microscopic level. And the bonding force is different for different elements or different material, I should say. So because of that, what happens is this friction coefficient is also different. So that's the bit details about the nature of the origin of friction force. For this class, you need to, use these two equations in suitable situation, like, you need to know when to use kinematic equation, kinematic friction force, and when to use static friction force, and when static friction force is maximum versus sometimes it could be zero, right? Hopefully you understand that. And so now, rather than giving you friction force in the problem, you may be given friction coefficient. So it may say, okay, the friction coefficient is this much. Is it static or kinetic? You may have to sometimes determine yourself. Sometimes you may be told. Okay. So hopefully now you know when to use static friction coefficient and when to use kinetic friction coefficient, or in what situation given friction coefficient is static versus in what situation it is kinetic, and in what situation friction force, static friction force, is maximum. Okay, so those three things you need to, it's like a new vocabulary for you. Okay, so anything you like to ask or add? Okay, then I have a question for you. So I'll open the poll. Simple question here. Being a very fast, I am giving you a 1 minute and 30 seconds. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see how did we do here. So B and C kind of competing each other. B got even more, one more vote. So greater than F. So it seems like, okay, we are pushing, it's not moving, so that force must be bigger, right? It must be pushing with a bigger force. That's what it seems like, okay? But just like we talked here in the slide, applied force and static friction force, since it is not moving yet, it is static friction force. So that means it is always equal, just like I have written it here, okay? Applied friction force, sorry, applied force is equal to the static friction force, okay? So that means C is the correct answer in this case, okay? So yes, it's easy to so there is a question on the chat that says, how do we know when to use coefficient of static or coefficient of kinetic friction force? Okay, that's a great question. Okay, I briefly talked about that. So static means as long as object is not moving or is just about to move, just starts to move. And for kinetic, when object is just sliding, okay, already. Okay, so now let's look at one example. Hopefully that will even clarify that question. So I'm bringing this problem here. This problem has a two-part, but I just brought first part here first. So over here is asking coefficient of static friction force because it is at rest on horizontal floor. And it says it just starts to move. So that just is like a critical situation, threshold situation. So it's talking about maximum static friction force situation. So when you hear, see, or read this kind of statement, it should click in your mind that you are talking about maximum static friction force. Otherwise, it would simply say, okay, this is sliding, okay? Rather than saying, okay, just starts to slide or move, okay? It would say, okay, it is moving, sliding, something like that. So if that's the case, then it's going to be friction, the kinetic friction force. But this is the maximum value of static friction situation. So if you were to apply a little bit more than that, it's going to accelerate, okay, and becomes kinetic situation. Okay, so now, since we have learned two main idea of physics, basic physics, I should say, kinematics and dynamics. So whenever you read a problem, you need to determine whether this is problems related to kinematic equations or dynamics or laws of motions, okay? So you need to determine that. So for that, what you have to do, you need to read the question first, see if that helps you just by reading once. But even better, you read and write things, the things that you know, you list them, for example, 3.0 kilogram, and then horizontally push with a force, there is applied force, 12 Newton, and then it's asking for coefficient of static friction force. So that means it's talking about this static friction force. That's what we want. And then we also know that this is related to this, which I just talked about using this equation. Okay. So these are the things we know about this problem. So based on this problem, can we decide whether it is kinematics problem? That means that one uses those three kinematic equations, or we need to use Newton's laws to solve this problem, okay? So that's what I'm asking you here. Very first step is to identifying what kind of problem it is. So sometimes I receive emails saying, okay, Ramesh, I learned the physics, I know physics, but whenever I try to solve a problem, I get stuck. So this is answer to that question, okay? So first you need to identify what kind of problem is it by carefully reading and listing the knowns and unknowns. Once you have that, you should be able to tell, how, what concept to use. And that's what I'm asking you to do here. Go ahead, and you have now a minute to answer this question. Thirty more seconds. Five more seconds. Five, four, three, two, one, and it stops. Okay, let's see what we got here. So mostly B. So it is, yes, dynamics problem because it has force and mass. See, in kinematic equation, there are no forces, mass, okay? Yes, there is acceleration, but there is no force, mass. In kinematic equation, there are initial velocity, final velocity, displacement, time interval, right? So those displacement, time interval, final velocity, we are not given, we are not asked to find here. So maybe that's, we don't need to use that, or we cannot use that. Rather, we need to use dynamics because we are looking for this, and this is in this equation, which is basically a force, okay? And we know force and mass, they are related by Newton's law. So that's the way to do it, okay? And by the way, here it says it just starts to move. So that means it's not already accelerating. So we can say, okay, acceleration in horizontal direction is 0. So it's a relationship between force, mass, and acceleration, and which is dynamics basically, right? So now that's the first step. You identify problem, which concept to use, right? And once you determine, you have to use dynamics or Newton's laws of motion to solve this problem. Next step is to draw free body diagram. Remember, the sum of forces means we need to draw the forces, and then that way we can tell which forces to add, okay, in the equation. So for that, we need to identify what forces are acting on our object of interest. So first we need to identify object of interest. So here, object of interest, how do you determine? So which object is moving or trying to move here? That's the object of interest here, okay? So in this case, it is a block. Block is the object of interest for free body diagram. So now, drawing free body diagrams means drawing all possible forces acting on object of interest. So what forces are acting on this object of interest? So remember, we have long range force, which is gravitational force or weight or mg, right? And then we have contact forces, possible contact forces. What are those? Could be normal force, friction force, and then tension force, and then some applied force, right? So what are those forces that's acting on this object? So that's what I'm asking you. So when you are solving this problem, you have to go through this. So it shouldn't take long, but that's the way you need to think. Your thinking process should be in this direction. So you have total 1 minute for this one as well. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see. We mostly got D. Okay. So A has a normal friction and tension. So since this is not being pulled by a string, so there is no tension force, so nobody chose A. So that's great. Normal applied and friction was B. 6 of you chose. So normal applied and friction. Okay. But see, weight is always there. As long as we are near the earth surface, what happens? Weight is always there. So it's missing weight, and C is missing. Now, let's see, normal friction weight, but the applied force is missing here. So D is the best choice here because of that. Okay. So now we identified the possible forces, all the forces that's acting on the object. So next step is to actually draw a free body diagram and then use, solve the problem using Newton's law. And actually, when you are actually solving, this is how it's going to look like, because those process you may go through your head, or you can actually, I suggest you write it down, especially when you are in the beginning phase of learning. Okay. So just like I was saying, this problem has two parts, but they are very closely related. So let's focus on A, which I already said. We already went through that. So for that, let's draw a free body diagram. Okay. So mass, there is only one mass in this case, right? Up to A, there is only one mass. Once we go to B, then we have two masses. So for now, just one mass. So I'm denoting that M by that mass by just M without any subscript. Yeah, you can denote that by M1, but you don't have to. I like to keep things simpler as much as possible. And applied force, as we listed, it is 12 Newton. So let's draw the forces. So we're replacing the mass by a dot, okay? Not box or anything like that, just a simple dot. And then one that's acting vertically down, or the weight always acts vertically down. Whenever the mass is given or we are asked to find mass, I like to write weight as m times g rather than just w, okay? And then there is normal force vertically up. Why? Because this thing is on horizontal floor. If something is on horizontal floor, then normal is vertical, because normal means always it's normal or 90-degree to the surface, right? So that's that. And let's say it's being pushed in this direction. So that's the applied force, okay? So now if applied force is in that direction, so that means object is trying to move in that direction, right? Means now friction is in opposite direction. So the friction force acts in the opposite direction of motion, or if already not moving, opposite direction which is trying to move. So if you are trying to push it to the right, then friction force must be opposing to the left. So this is that, and this is, since it says it just starts to move, it is static friction force, and it's the maximum value at that situation, okay? So this is our free body diagram, but since we want to write the equation in horizontal and vertical direction separately, what we do is we choose axis and say this horizontal direction. So let's say this is positive x, and for vertical direction it's going to be y. So let's say up as a positive, y, okay? Positive y. So now, looking at this, what happens here? All four forces are either along the x direction of our choice and y direction of choice. Ideally, that's what I like to see, we like to see. But sometimes there may be a force, one or two, that's not acting either along the x or y of our choice. In that case, what do? We need to find component of that force in the x and y direction. So that's why being fluent on writing component is important even for dynamics. So it's not just about the kinematics, it also about the dynamics. Okay, so now we have this. So once we have free body diagram, we can start writing equation. So should I write in x direction or y direction? So if I write in y direction, I have a normal force and weight. But here it's asking us to find, in part A, it is asking us to find coefficient of static friction force. And by the way, coefficient is neither maximum or minimum. It's always fixed for a given two surfaces. We call it constant. So that's why it is a coefficient and it's a constant. Okay. So this is what we want, but we know that that thing is which is in Fs max, right? That's where it is hiding. Okay, it's hiding there. So we need to peel off one layer so that we can see it. See, that's where it is. So that means we are interested in this force, which is along the horizontal direction. So let's start by writing equation in horizontal direction. So sum of forces along the horizontal direction is equal to mass times acceleration in that direction, right? So I always first write the main equation that you can actually locate in equation sheet, okay? So now this is sum of forces along the x direction or horizontal direction. So can you count and type how many forces are there in horizontal direction in this free body diagram? Is it 1, 2, 3, or 4? I'm just talking about horizontal direction. Okay. So there are 2. I received some responses there. Thank you for, being attentive. Hopefully others who did not respond also paying attention. Okay. So there are 2 forces. So I like to start writing by writing the force that is pointing in the positive direction. So F is pointing in positive x direction. So that's why I'm writing this as a positive F. And then friction force is opposite of that, means it's going to have negative sign. So 2 forces. So this term here means sum of forces in that direction. So that means we already added 2 means all. So that means left-hand side is done. For right-hand side, mass times acceleration. So it is just starting to move. Even if it was moving, it may be, let's say, like in this case, it says just starts to move. So it hasn't started moving, not accelerating or anything like that. So we can say acceleration is 0. Okay. So it is still in equilibrium condition. So now I want Fs max. So that means let's solve this one for Fs max. Actually, I want mu s. So let's replace this Fs max by mu s times n. So now let's solve for mu s. So I like to write that one on the left-hand side. So n goes to f underneath f. So this is going to be f over n. Okay. So need n. F is already there. Okay, we already know what is F. So we need N. So to find N, what do we do? N is a force, normal force. So to find a force, we need to look at the free body diagram. So when we look at the free body diagram, what do you see? It is right there in vertical reduction. So that means we need to write equation in vertical reduction. In other words, I need to write this equation now. I need to complete this equation. Okay. So in vertical reduction, there are just two forces as well. So positive N, and then mg is negative because we chose up as a positive. Why? Okay. So here as well, acceleration is 0. It is not accelerating in y direction. So that gives me normal force is mass times mg. So now with that, what I can do is go back and use that since we needed that, right? So F over N, but we just learned that N is M times G, weight of the object. So I can do that. So I know both, all these three things. Force is 12 Newton. Mass is 3 kilogram, 3.0 kilogram, I should write. And then Z is 9.8 meter over second square. So this kilogram times meter over second square, when you combine these two units, it's a Newton. So this Newton here cancels with this Newton, leaving this unitless as it should. Okay. So now when you work with these numbers, turns out you get 0.41 when you round it to 2 sig fig. Okay, so this is 2 sig fig problem because it has a 3 sig fig here, but everything else has a 2 sig fig. So we round it to 2 sig fig. Okay, so that's the part A of the problem. How about part B? So in part B, what happens now? There is this mass, and now 7 kilogram mass goes on top of that 3 kilogram mass. But this 3 kilogram mass is still in contact with our original surface, right? So the friction coefficient gonna be still same because friction coefficient simply depends on what surfaces are in contact. The surfaces that are in contact are still same, okay? Only thing changed is that now on top of this block here, there is another block on top of that. So the contact surfaces are still same, means friction coefficient is still same. So for part B, so I'm not gonna go to another slide. I don't have another empty slide. I'm gonna just modify this and see how this problem is very same, okay? So I'll try to do it a bit quicker. So I'm writing it here, but if you are copying this, you should do it after all this underneath, okay? So now for this, we can use this we found from part A, okay? So now what are we asked to find? In this case, we are asked to find how much force we need to apply, okay? And what do we know now? Mass. There are two masses. So let's say both two masses, m1 plus m2, both, okay? And we know one is 7, another one is 3. So 10 kilograms. So let's write this way. so that we're not making it to just one sig fig. We know we have just two sig fig here, so we can write something like that for the mass. So now with that, next step is that the only thing that changed is this. And you know, the mass means weight changed here in the free body diagram. I'm recycling the same free body diagram. Everything else, their value are different, but notation, we still using the same. So that means I'm keeping that free body diagram. So that way I can see now how I can use that. So in this case, we want applied force, okay? And again, the applied force is related to this, you know, let's say opposite to this friction force. So we can use this equation in the x direction and use the same equation basically, okay? Same equation, and Fs max is still this same thing, okay? So this side is still same. What changed is that normal force, value of normal force going to be different. Why? Because mass is different. So how do we do that? So again, we use the equation in vertical direction. So what changes? The notation of this mass is now uppercase M, I'm writing, which includes both masses, okay? So yes, you can even just use lowercase mass for the notation, but if you decide to do that for part B, make sure you are using the total mass, not just the 3 kilogram mass, okay? So I will stick with the uppercase M. So now, okay, so in this case, oh, we don't even need this one here because we're not solving for mu s. So all we need is up to this point. So yes, need n. Okay, and for that we go through this. So now this part gets slightly modified here. Means the applied force is mu s times n. So n in this case is uppercase M times G. So 0.41 times 10.0 kilogram times 9.8 meter over second square. Again, these two units are going to combine and give you now unit Newton. Okay, so it looks like we get around 40 newtons here. Yeah, not a, I think we need to round that to 2 sig fig. How do you do that? Maybe you put 1 decibel over there, okay? So if this kind of situation arises in your canvas, you can do, you want to type 40 point, let's say, yeah, 0 or something like that. Yeah, unfortunately, Canvas is not very good at this particular kind of, you know, sig fig problem. But I put the error margin so that, you know, that not going to make difference in terms of your answer being correct or not in this kind of situation. Okay. Oh, looks like it's already break time. So I will leave it here, folks. So if you have any question, let me know, or else I'll see you in 5 minutes, okay, after the break. Welcome back, folks. So we are learning how to use laws of motion to solve problem. Starting, you know, we started that last class. And then here, one thing we are doing special is we are including friction force where friction coefficient is given, okay? So far we have learned two main concept of the basic physics, and we always have to think whenever you see a problem, you need to think in terms of, okay, what basic physics concept I can use to solve this problem, right? So in this case, I am again starting by, pointing out what are the important steps you need to look or go through while solving uh, or using Newton's law to solve any kind of problem, not just this problem, okay? This is just an example. So if you pay attention and follow this, you should be able to solve any problem using laws of motion. And you have already learned how to use kinematic equations, right? So, and I had this kind of steps, multiple steps, and steps, and with several clicker question in one of the projectile motion problem. So let's start by identifying what kind of problem it is, okay? So I'm giving you a minute to answer this question, okay? As always, I'll write down what are the things, we know. That's what you should do. Oh, forget to 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got. So again, see, there are no initial velocities, final velocity, displacement, or time interval. Neither those, mentioned here or asked to find. So that's why it is not kinematics problem, it is dynamics problem. Okay. Okay, so we identified this is another dynamics problem. So that means what's next? Identify object of interest and draw a free body diagram, right? So to draw a free body diagram, we need to identify all the forces acting on object of interest. Here, what is moving or trying to move? It's a dog. So that means object of interest is dog, not slide. Okay, slide is just surface on which the dog is sliding. So when we have inclined plane, just like we had in last class as well, we pushed a block on inclined plane. So to draw a free body diagram, what did we do is, as a reference of inclined plane, we basically draw an inclined dash line. Doesn't matter which way it is inclining, this way or that way, okay? So let's say this angle is theta. So you can replace object by a dot on the incline and you can start thinking about what forces are acting on that object, okay? And that's what exactly this next question is. And you have a minute to answer that question. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got. We have A and C mostly. There is a little bit B as well. So weight is there, of course, always. A normal force, it is on the surface, right? It is on the surface. So that means there always going to be normal force when something is on the surface, supported by some sort of surface. And in this case, it says friction coefficient. So that means there is friction as well. So that checks, check. Acceleration, it's asking for acceleration. So acceleration is there, but acceleration is not a force. So it does not belong on that dot. So you're not drawing acceleration on the dot. So that's why this is not a good idea. Okay. Let's look at another one. So it says tension. So since the dog is not tied with a string or being pulled by a string, so that's why this is not a good choice. So turns out C is the best choice in this case. Okay. So we identified that there are 3 forces acting on the dog. So this dot being the dog, so now you need to draw those forces, right? How would you draw those forces? So here are some choices. Go ahead and choose which one, how would you draw those forces that we identified? Forty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. D and E mostly, and there is B as well. I just noticed there isn't much difference between B and C, huh? So we identified that there are only 3 forces acting. So one with just 2 arrows or 3 arrows. Oh, 3 means yes, 3 are possible one. The 4 arrows, those are not the possible free body diagram. So these don't have normal force, okay? But there is normal force here, which is perpendicular to the surface. So that's why E is the best choice in this case, okay? So you may be wondering, since this is accelerating downhill, there must be a force downhill. See, we don't see anything. Remember, it has to be contact force. Nothing is pulling the dog down, okay? So we cannot just draw that force there. If something is not touching, not applying that force is not there, okay? Okay, so now, once we have something like this, we need to choose suitable axis, one axis suitable. Once we choose one axis suitable, another one is always perpendicular, no matter how you choose it, okay? So for that, I am giving you some clue here. Choosing one axis in the direction of acceleration makes it easier to solve dynamics problem, okay? So what is the direction of acceleration of the dog in this case then? Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. Down along the slide, that is correct answer. Okay. So this dog, if it's accelerating, it's going to accelerate along the slide. Its motion is along the slide, of course. Okay. And since it's not being pulled up or anything like that, it's not going to be accelerating up along the slide. Okay. So down along the slide makes best sense here. So now what I did was I drew the coordinates here, and that's what you should do. So I'm choosing down as a positive. Yes, so you can choose up as a positive if you like, but I like to choose positive in the direction of acceleration. Okay, whatever direction the acceleration is, I like to choose positive in that direction. That way, when I'm writing the equation with acceleration being always positive, that mass times acceleration always, that term in the equation always going to be positive. Okay. But here in this case, we are just finding the acceleration. So even if we don't write the sign of the acceleration, we're going to be fine because we're going to be solving for it. Okay, acceleration. So the acceleration will have both value and direction. But that may not always the case. So that's why, remember, this is just one example, but the same method can be used to solve any uh, problem using Newton's laws. So in the last problem we saw object was, sliding or trying to slide horizontal direction. So we learned how to use Newton's laws in horizontal direction. Last class we talked about how to use it in elevator, and even at the beginning of today's class we looked at when masses are going up and down. So that means how to use that in vertical direction. See how I'm covering all these? We learned how to use Newton's laws in vertical direction. And the last problem was about using Newton's law in horizontal direction. And this is again about using Newton's law in inclined plane. So all three, the three possible scenario I'm talking about. And that's all we need to know. Okay, those are the three different scenarios we possibly can have for this class. So I'm covering all these. And this problem is also done in detail in my note that I provide you folks, right? So I chose the x-axis along the incline, and I chose down because acceleration is down as a positive because acceleration is downhill, okay? And then y always gonna be normal to that x, okay? That's how the x and y coordinates work. Once you fix x, y has to be always perpendicular. So it's going to line up with the normal force. So what do we see here? Is that normal is lining up with the y-axis. Friction force is lining up with the x-axis. Okay. And the mg is not lining up with any of those axes. So now the question is, based on the chosen coordinate system, which force in this free body diagram needs to be written in terms of its components? Okay, so what do you think? For this, you have only 30 seconds, okay, folks? Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see how did we do here. So mostly mg, yeah, the one that's not pointing along the x or y direction of our choice, we need to find component of that one, right? So this is a vector quantity. It has a value mg and direction is pointing down, but we want direction either from x-axis or y-axis in terms of angle, okay? This or that, which one we know in this case. We know we are given this angle here. Which one does that corresponds to here? So for that, we can take clue from what we learned, last class as well. So this is the angle theta made by the inclination or the slide with the horizontal, right? So that's given. So whenever that angle is given in the free body diagram drawn like this, it's always that angle going to be same as the angle made by this weight force with the y-axis, not with the x-axis, but y-axis, okay? So now once we have the angle, so we should be able to write this component and that component now. See, these are components. So they were not there. These two were not there. See here? So we are drawing free body diagram knowing that, okay, this way, that way. Remember, this has to go parallel to this x-axis, right? So this is our y component here of the mg, and this is the x component. But rather than drawing here in free body diagram, we want to draw from the dot. So that's why we are drawing it there, okay? So that's what I'm doing here. So now I'm asking you to figure out which component is which, okay? And it says x and y components respectively. So first in the list, the correct one will be the one with the x component, okay? So for this, I'm giving you a minute and 30 seconds. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here. Mostly C. Okay, looks like that is a correct answer. So this being adjacent side here is gonna pick up the cosine. And this now becomes opposite, right? So that's opposite, means this comes from the opposite. So once you identify one is cosine, another one is sine. So mg sine theta. Since this is pointing downhill, and we said downhill as a positive, so this is positive mg sine theta, and that's what we are writing first. And then this is negative because it's pointing opposite to positive y of our choice. Okay. So we don't write positive or negative sign right here in the free body diagram. Okay. Some may write it, but I don't suggest, I don't ask you to do that. Don't do it. Why? Because the direction is right there. The arrow is direction, this value. That's how I like to write that in free body diagram. But when we are writing that as an equation separately, then we need to include those signs correctly over there. Okay, so we almost there. It's time to write Newton's law eventually. See how much thinking process and skill we have to use, okay? So now we have nice free body diagram with the required or necessary free body diagrams. So now what happens is we want to use that in the x direction, second law of motion in the x direction. In other words, we want to expand this equation for this free body diagram. Okay, so which is the best equation here? So again, you have a minute and 30 seconds for this. So you are just expanding this by just looking at the free body diagram. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. So mostly D and better be, that's the correct answer. And it is. So how do we go about it? So there are how many forces in the x direction of our choice? There are 2 forces along the incline, okay? So that means to expand this, mg sine theta is pointing downhill and that is positive. So I like to write that one first. And then Fk is opposite of that. So that's that. And that is equal to mass times acceleration. So in this case, dog is accelerating downhill, we said, okay? So since we are calculating acceleration, we could just write max, or since we know the direction, we can say, okay, that's that. Or we can even just write now positive m times a, where a is the value of acceleration. Direction we already know, downhill, okay? So that's that. So that's how that equation comes in. Now here is this friction force. Here, friction coefficient. So they are not same. They are related. So we need to replace that by this mu k times n. But what is n? So now need n, just like when we did that in horizontal case, right? We need n. And now n is in y direction. So for that, we need to write this equation in y direction. And since it's not accelerating in that direction, we can say, okay, net force along the y direction is 0 and positive n negative mg cosine theta. Looking at the free body diagram, 0 means n is, see here how n is not just mg, but mg times cosine theta. Okay. So normal force is not always mg. It is mg only when something is sitting on horizontal surface. But even that case, what happens is if it's being pulled by some tension force at incline, then it's not equal to mg. Probably you discovered that while doing the worksheet that was due, this week. So that's how this friction force can be found from the friction coefficient and normal force. So that means it becomes mu k times mg cosine theta. So you want to replace this by that and solve for a. So anyway, so that thing is done here. So see how I talk about all these details and why we go about it. See how what forces are acting. And of course, this is acceleration, not the force. And then free body diagram, okay, with the components, and then equation. So you're solving for acceleration. So Fk, you need to use that mu k times n, which I have done in the note in next page, and so on, okay? So it's done in detail over there. So now, see if you can do it without looking at the solution. Just look at the question and see if you can do it, okay? And if you can do it without looking at solution, that means you learn how to use Newton's law, okay? And there are other problems done in the note as well. So you want to do them without looking at the solution, see if you can do it. So that way it tells you, okay, that's the way to find out whether you have learned, okay? And do not just read through the problem, or do not just keep this, solution open and go back and forth while doing it. So what you want to do is, if you have to look once and set that on side and see if you can do it on your own, okay, without looking at it. So that's how you need to practice to solve problem. So these are two main ideas. One, laws of motion, another one, kinematics, right? So you should practice, from the slide. I have done, similarly with the several, multiple choice questions. I did that for the kinematics problem where it was the projectile, okay? And here I did for one of the most complicated problem that we do in this class. So hopefully you understood that, and now you can do it. If not immediately, then with some practice. Practice is always necessary, okay? So I try to make it as interactive as possible by bringing this lot of questions, okay? Hopefully that helped. So now we want to include another kind of force. For example, sometimes we may have a drag force. So we talked about air resistance before. So drag force is basically air or water resistance. Okay, resistance in motion from either air or water. When something is trying to move or moving on the air or in the water. The friction is the, opposition or the resistance when something is trying to move on solid surface. Here, if something is trying to move in fluid, or fluid means liquid or gas, then in that case what happens is the friction force that we learn, like Fk is mu k times n, is not correct. So we need to look at a little bit more detail, and that's what we are talking about. So what happens is when we drop something, when something is falling on the air or inside the water, what happens? It accelerates, right? So it's falling, it's kind of, if there was no air, it would be in free fall, value of acceleration would be g, but that's not the case now because there is drag force acting upward. So the value, the acceleration not going to be equal to g. It's going to be less than that, okay? So how much is the acceleration? If you want to find that, we need how much is drag force. Once we have that, we can use that and find the acceleration if needed or other things, okay? So when something you drop, what happens? If this one here, piece of paper, if you drop something like this, it's going to fall a little faster than when you drop it flat, okay? So that's what I am trying to show you when, oh, fall is there around the corner. So when a leaf is falling, and if it is flat, then it falls really slow, okay? So drag force is acting. So at the beginning, it's accelerating, and it is accelerating downward, means the velocity is increasing, okay? And how much drag force acts depends on how big the area, we call cross-section area in this case. So for example, when my hand, for example, is falling something like this, that means only this much area is exposed to this blow of air in the backward upward direction. But when my hand is like this, then this whole area is exposed to the blow of air, upward draft of the air. So that's the area we need to look when object is flat like this, but when it is something like that, then only this area matters. So larger the area, what happens? It drag force becomes smaller. So that's why when you drop paper flat compared to this, what happens? It falls slowly. Okay. So now another thing is running in water is more difficult than running in air. So why? Because air is more, sorry, water is more dense, okay? Larger the density of the object. We'll talk more about density in yet another chapter. For now, if something, if you have two objects and one is, same size two object, but one is heavier than the other, that means the one that is heavier, we say it's more dense. So that's why it is more heavy, right? So that's how we use the density here. And then what happens is, unlike the friction force, the drag force depends on the speed. So faster it is moving, more drag. For example, when you stick your hand outside from car window and go faster and faster, what happens? The wind blow or resistance from the wind you feel gets larger and larger. So when we include all those factors, what happens? That's how the equation looks like. Okay. So to identify drag force, I have written this as a, with the D subscript. Okay. And this is, we call, drag coefficient for the material. So it's like a it's like a, in this friction equation, we have friction coefficient times normal force. So it's like that constant here that depends on the, size and shape of the object. but they are, you know, their values are not same, of course, mu k versus c. So that's why the notation is different. But that is the drag coefficient we call, just like we said friction coefficient, okay? So now if we want to draw a free body diagram of falling object with a drag, we can draw something like that. And what happens is when something drops, sometimes it may stop accelerating. So that means the net force is 0. So what are the forces acting? Drag force and the weight of the object means they are equal. Okay. So we can write equation something like, you know, this is equal to that because acceleration is 0. So that means they are equal, right? So that velocity, the velocity, so at the beginning, velocity is increasing. After a while, what happens? Velocity becomes constant. That velocity, when it becomes constant, it has a special name we call terminal velocity. Terminal because it's not increasing anymore, right? Kind of makes sense. So after that, that velocity becomes constant. So you can solve for such velocity if you know these parameters, okay? And if object is kind of bit regularly shaped, you know, nice round object like this, then this equation of the drag force becomes even simpler and comes with even a small, you know, a special name. And you see here the friction coefficient or drag coefficient kind of situation, you know, the equivalent of that is this, what we call eta. And now rather than area cross-section area would be pi r square. But now rather than r square, we have just r here. And similarly, rather than v square, we have simply v. So the drag force for this regular object becomes, you know, bit way smaller than the irregularly shaped objects, you know, like big flat object like this. So that's why the drag force on the bigger watermelon versus honeydew was, you know, not that much, okay? Because of this reason we saw, you know, whatever that was, there was not much difference. So heavier watermelon and the honeydew fell side by side in one of the video we watched in pre-fall class, okay? And another force is, so I did not bring problem. So here is an example over there, okay? And there is this kicker question, but we're running out of time. So in this case, of course, we are making area smaller in this case, so I'm not gonna pull on this. Rather, I like to move on another force we call a spring force. So when we pull a spring, what happens? Because of that bond being raised and pulling it back, it's the spring force. So it is not, you know, it is not just on the spring, but similar force exists in the bone and the rod and something like that. And that is the kind of origin of the tension force as well, basically, if you look at it, okay? So that force is given by what we call Hooke's law, okay? So what that means is more you stretch, larger the force becomes. Try pulling a spring and you will notice that immediately. Pull less, the spring is pulling you less, and pull more, what happens? The spring is pulling you more. So mathematically we write that, but this is called proportionality sign. So we want to write that in terms of equal sign. So what do you see is to make it equal, we need to put a constant, what we call spring constant, okay? And this negative sign simply means the displacement and the spring force, they are in opposite direction. So X down, so spring force is up. But applied force and the X, they are in the same direction, okay? So what this is telling you is when X is double, this force is also double. When X is triple, this force is also triple, and so on. It's proportional. So the force, spring force, is proportional to the stretch on the spring. So that's what it is basically saying, okay? It's 51 already, so I'll let you go, folks, okay? We'll talk about this and a little bit more in another class. Okay. And then, by the way, if you have any question, you stick around. Since I don't have office hour today, I can stick right here in this Zoom room a little bit longer.